Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. My name is Amy Draves, and I'm here to introduce and welcome Frank Close, who is joining us as part of the Microsoft Research Visiting Speaker Series. Frank is here today to discuss his book, The Infinity Puzzle, Quantum Field Theory and the Hunt for an Orderly Universe. 40 years ago, a group of scientists made breakthroughs which later inspired the construction of the LHC, a multi-billion-dollar machine which may be on the brink of revealing how the universe itself came to be. Frank Close is a professor of physics at the University of Oxford and a fellow of Exeter College, Oxford. Author of 10 books and over 200 publications, he has lectured on every continent except Antarctica. Please join me in welcoming him to Microsoft.
Thank you. Well, thanks very much. It's a bit of an imposing title, and I hadn't really got an idea what the audience was going to be. But the subtitle really could be this: From Atoms to the Large Hadron Collider. It's really this today is the story about how two of nature's forces were united. And they were united by something called hidden symmetry, which I shall tell you about, and the boson that's named after Higgs. I think everybody's heard about the Higgs boson, which is costing $10 billion to try and find, except it's 10 billion euros, not even dollars, and the euro's going down fast, so it's getting cheaper by the day. But why it's named after Higgs and what it is anyway is an interesting one. He modestly calls it the boson that's named after me, to put something context in it. The two of the forces that were unified, that started this whole thing off, it's really about 50 years ago. These people, Weinberg and Glasgow at the top, a photograph taken a long time ago for those of you who know these people, and John Ward and Salam at the bottom. What is it that they had done? They had built what we now call the Electroweak Theory. This was a theory that combined electromagnetic interactions, the things that hold you and me together, make compasses work, operate the Wi-Fi that many of you are looking at and not looking at me now. And the weak force, which is responsible for a form of radioactivity in particular that changes one variety of element into another and plays a very important role in the way the sun works. They brought these two together in a mathematical sense that I'm not going to talk about for those of you who know the words SU2 cross U1, but it doesn't matter. The thing is that the electromagnetic force is transmitted by photons, which are the quantum bundles of light which have no mass at all. The analogous things that work for the weak force are called W for weak, W and Z, and they're very massive. So the fact that they are massive, whereas a photon is massless, immediately spoils the idea of symmetry that was behind it all, and that's what I'm going to talk about. It also created horrible things that the moment you tried to calculate with this theory, it gave you infinity, which is what the book is about, and I'm not going to talk about. I see, and if I talk for more than 30 seconds, it disappears. Okay, right, on my screen. So when did they do this? Well, the first person of this group was Glasgow at the top right there in 1961. Then down the bottom right, Salam and Ward in 1964. And up top left, Steve Weinberg in 1967. And this is where we have a problem, which is this. This was clearly going to be Nobel Prize work, but Nobel Prizes can only be given to a maximum of 3, and people who work at Microsoft know that 4 is greater than 3. And the prize was awarded to Glasgow, Salam and Weinberg, and not Ward. And it's been somewhat of a cause célèbre in physics ever since as to whether Ward was justifiably not included or whether he was airbrushed out of history, as many people have argued. And I discuss that to some degree in the book. I'm not going to go into details about it today, but I'll whet your appetite, maybe. Then we come to the other half of the story, which is how people manage to get mass into the whole idea and bring things much nearer to the universe as we see it. And this is associated with Peter Higgs, the father of the Higgs boson, again, ironically, in 1964 when he had that idea. So it's half a century ago that these ideas first emerged, and only now have we got to the point technologically of being able to do experiments to really show one way or the other whether nature does this or whether it's just a mathematical game. If he was the end of this, that would be easy, except that that same year, and as we will see, within the space of a couple of months, 5 other people also had essentially the same idea. And these 6 have become known as the Gang of 6. And there they are in sort of passport photograph mode. And of course now there is an issue about if there are Nobel Prizes to be awarded, if and when the Higgs boson, whatever you like to call it, is found, then there is a real problem because 6 is much greater than 3. And there are already a lot of discussions about how things should be apportioned and arguments and those for and against, and I will air some of those. So let's just go back a little bit to set the background for people who know nothing at all about this, which is bound to be several people, but it's this. First of all, how do we know what atoms and their innards are made of? Well, we look at them. You're seeing me because light shines on me into your eyes. In the jargon, there's a beam, there's a target, and there's a detector. To go and look at the innards of the atoms, what we had about 40 years ago was a beam of electrons, which is 3 kilometers long, a target of hydrogen, whose nuclei are protons, and a huge electronic detector to see what happened when the electrons bounced off. And that's the sort of setup. It's at Stanford, just about 900 miles south of here. The electron beam came out of that tube. It appeared out here. Behind the concrete is a target of hydrogen. The electrons bounce off into that detector, and that is me. And you can see it's me because it's got hair on, because that was taken 40 years ago. Anyway. As a result of those experiments, what they found was that the proton is not a basic seed of the cosmic onion. There's another layer inside made of quarks. So the discovery of the quark layer of reality came as a result of those experiments at Stanford about 40 years ago. To make a proton, you need 2 up quarks and a down. To make a neutron, 2 downs and an up. If you're typing the numbers in quick, you'll check that 2 lots of plus 2/3 take away minus 1/3 gives you plus 1, which is the charge of the proton and so forth. They're called up and down. They don't look like that, as far as we know. And those 2 seeds make the heart of all atomic elements and everything that we have around us here. The electron whirling around on the outside of atoms is not made of quarks. If it's made of anything deeper, we don't know what it is. It's, in present understanding, independent of quarks. And yet, there's an amazing conspiracy that we see all the time. The fact that as we walk down the street, breathing in and out, our hair doesn't go up and down, is because we are electrically neutral. I mean, you know, these old tests you see people do at open days, you put them on an insulating plate, charge them up, the hair sticks up, for those of us who've still got it. And the fact that it doesn't is because we are electrically neutral. The negatively charged electrons in all of our atoms are precisely balanced in electric charge by the positive charge in the nucleus carried by the protons, which sounds no surprise until you learn that the proton is made of 2 up quarks and a down. The up quark having 2/3 of an electric charge and the down quark minus 1/3, and that they combine together in 3s. An amazing conspiracy that 3 times exactly 1/3 electrical charges counterbalances the negative charge of an electron. And yet we are understanding that the quarks and electrons know nothing about each other. Clearly they do. It's just too much of a conspiracy. But precisely what that is, we don't know. But I give that as an example that sometimes very simple things, like your hair stays in place when you breathe in and out, can be pointing towards very deep, profound truths in there. That, I doubt we will answer at the LHC. That's a problem for you guys to worry about a few years from now. Okay, so what has this brought us to? That the heart of matter, as we know it, has electrons whirling around up and down quarks. There is also a beast called the neutrino, which is like an electron with the charge removed. And that left-hand column up here are these characters. However, nature is not satisfied with that for some reason and has reproduced them twice over. That the electron, negatively charged, has got 2 more massive counterparts, identical in all respects except for their mass, the muon and the tau. The neutrino comes in 3 varieties with different masses. The down quark has got 2 heavier analogues and so on. The up and the charm have a heavier analogue, which I didn't want to show until now because it would swamp the screen. That gives you an idea of the relative masses of these things. You don't need to know all the names. The message from this transparency is much more simple. That there is a symmetry at work, an identity between up charm and top, or between down strange and bottom and so on, broken by the mass. If it wasn't for mass, there would be a beautiful similarity here, but mass has got in the way. The same thing is true for the way that the forces work, apart from gravity, about which I'm saying nothing. The electromagnetic force is transmitted by photons. And mathematically, QED, the quantum theory of that, is called a U1 theory. The force that grips these three quarks together, we now say is transmitted by gluons that glue them in place. And they are just like photons, no mass at all, except there's 8 of them, and mathematically it's exactly the same as QED, but with an SU3 mass to it. The weak force is this thing up here, and that is exactly the same game. It's transmitted by W's and Z particles, and mathematically it's the same game, but with SU2. But the difference is this, that in the case of the SU2 part of it, mass has spoiled the symmetry. W and Z's are very, very massive, whereas the photons and gluons have got no mass at all. So both for the particles and for the forces, we are finding a beautiful symmetry in the underlying mathematics, which is spoiled by mass. And that is the sort of strategy that's been trying to be understood for the last 50 years. So the two parts of the story, the underlying symmetry found by these gentlemen back in the 60s. So how was it then that Ward got airbrushed out of that part of the Nobel Prize? Well, he certainly got airbrushed out in the literal sense. This photograph here of him and Salam appears in in Trieste, which is the institute in Europe that Salam founded. The brochure there looks like that. And I would have thought, out of all the pictures they could have chosen, it's rather ironic. So there's a literal airbrushing, but the question about why was he omitted, well, this is really what the prize was awarded for, as far as I can deduce. The Nobel Foundation keep these things under wraps until I think about 2026. So it's certainly, without any doubt, up the top left there, that Glashow and Weinberg, without any question, made contributions which were before anybody else, in the following sense. In 1961, Glashow was the first person to recognize that you could build this picture by using this SU2 cross U1 game. So he gets a tick for that. Ward and Salam, together in 1964, rediscovered what Glashow had done, but 3 years after somebody else had already published, bad luck. In 1967, Weinberg was the first person who also independently rediscovered the SU2 cross U1 model, but in addition, he realized that the trick of introducing mass by hidden symmetry, which is going to be the other part of our story, could be incorporated to do very interesting things. So he was the first person to, if you like, put the whole thing together, the symmetry of the SU2 cross U1 and this way of hiding it. So what then does that leave us with Ward and Salam? Well, Salam in 1968 also announced how to incorporate mass by this trick of hidden symmetry. But of course, again, those of us who know how to count realize that 1968 is after 1967, though not by much. But nonetheless, that's what he did, and it seems to have been his Nobel ticket. And Ward, of course, wasn't involved in that bit, and that's, I think, where he got lost. Now, the question that then remains is, was it justified to include Salam for something that Weinberg had already done or not? Interesting question, and I don't have an answer here at the moment, but that, as near as I can understand it, is why Ward got left out. I don't think that he had any real claim to be included in this prize. That far is fine. Whether Salam was lucky to be included is another issue. But that is the history of that part. But really it brings us to the nub of the talk. What is this business about getting mass in by hidden symmetry? Because that is the controversy, if any, that's going to come next. Because of the fact, as I said, that the people who realised that part of the story, there are 6 of them. So what I want to really talk about is the idea of symmetry and how it gets broken. and hope that the symmetry of my voice doesn't break before the end of this. It's beginning to disappear fast. So there are two types of asymmetry. One is this one here. This is the front of Peterborough Cathedral, the town that I come from in England. At first sight, you get a nice sort of symmetry in there, and then you notice that behind the front there is a tower on one side, but not on the other. And I don't know whether you feel that there ought to be a tower on the other side balancing it or not. One sort of feels that, oh, well, why is there a tower on the north side, not the south side? There's no reason why there should be at all. But there's something aesthetic that makes you feel there ought to be, and you sort of notice when things aren't symmetric. But that is actually a case of where there isn't symmetry, full stop, or period. The other type of symmetry, which is much more interesting, and we now realise is very far-reaching throughout nature, and in particular, we believe, is the seed of all of this business that we're now chasing at the LHC, is what's called hidden symmetry, sometimes called spontaneously broken, but hidden symmetry is the way I like to think of it. We now believe it's the key to structure for the fundamental particles and the forces of nature, and this business about mass is the example of it. So what is hidden symmetry, and why have we got a picture of a galaxy up there? Well, galaxies are pretty, that's why I've got them up there. But the thing is this, that the force of gravity between two massive objects depends only upon the distance between them, as the inverse square of the distance between them. It doesn't care what direction. So the force of gravity should act the same in all three dimensions. Therefore, you'd expect that anything collapsing under gravity would form a sphere, for example, like the sun. So the fundamental three-dimensional symmetry of the forces of gravity would lead you to expect spheres. And, of course, that isn't always the case. For example, in a beautiful spiral galaxy, you've got a lot of structure in a plane, but nothing out of it. So if the only thing that you knew of was a spiral galaxy, you might think that gravity acted in a plane. So this is an example of the true symmetry, which is three-dimensional, being hidden in some of the things that end up. If, however, you look at the universe as a whole, there's lots of galaxies out there, lots of spiral galaxies. The one at the top is one that's face on to us. The one at the bottom is one that's horizontal to us, and all angles between. So if you look at the hundreds and thousands and millions of galaxies that are spiral galaxies out there, they are oriented every which way. So the three-dimensional symmetry of gravity is present over the universe as a whole, but individual galaxies hide it. That is the sort of idea that is behind current ideas about what's called the multiverse, the idea that there are 10 to the 500 universes out there, whatever those words mean, and that the basic rules that govern them have been broken in different ways in each one. And we happen to be in one where the electron just has the right mass that we can be here having the conversation. I've no idea whether that's science or not. I don't want to talk any more about it, but there are people who are crazy enough to do so. You can invite them. A more serious example, though, to bring this thing closer to home, is when water freezes. That if you look at the surface of a perfectly flat glass of water, you're seeing complete rotational symmetry. The molecules could be anywhere around that circle. If you now freeze it, you get a different sort of symmetry, which is that of the snowflake. And here, you've got the nice six-fold symmetry. The snowflake here is with one of the dendrites pointing up at 12 o'clock, and here at 1 o'clock, and it could be anywhere in between. So each individual snowflake hides the underlying fundamental rotational symmetry. If you look at a window pane in the middle of winter, you will find these little snow crystals oriented every which way. So the window pane as a whole preserves the overall symmetry, but each individual one breaks it. Which begins to move towards the question, why does this happen? And how does it happen? Well, sometimes symmetries have to get broken, otherwise you have problems. For example, driving on the road. In principle, you could choose to drive on the left or the right. There's no fundamental symmetric reason to preserve one or the other, except that it is far more stable if you make a decision one way or the other. And in the UK, we drive on the logical side, which is the left. And it's also true that the UK's colonies and Japan, for some reason, do. On the right, USA, as one of our former colonies, France and revolutionary countries all drive on the right. There is a reason for this, incidentally. And I don't know if anybody knows what it is. Well, I asked this once in a class of school kids, and one of these kids put his hand up, me, and I said yes. Is it because in America the steering wheel's on the left? And in America, which the answer is yes, but the whole story. Okay, I will tell you, there are more right-handers than left-handers. And it turns out, apparently, that those of us who are right-handed tend to lead with our left leg. So if you go back like 400 years when people used horses, you get onto a horse and you lead with your left leg, and then you whip your right leg over and you go off on the left-hand side of the path. And the peasants who don't have horses have to walk on the right. In the French Revolution, the peasantry then did away with all of the things that the toffs did and decreed that they would go on the right. So my remark about revolutionary countries is actually not exactly a specious one. You believe that? You believe anything? Okay. But the real question for science is, why does this happen? Where does it happen? And how does it happen? And this has actually plagued people for centuries. And this is known as Buridan's ass. In fact, apparently it goes back to Aristotle. But anyway, Buridan was a philosopher about 500 years ago. And he worried about the sort of things that philosophers worry about. Namely, he imagined a perfectly symmetric donkey exactly halfway between two identical bunches of carrots. And logically, it therefore implied to him that there would be no way that this perfectly symmetric donkey could choose the carrots on the right as against those on the left, because that would break an obvious symmetry. Therefore, the donkey would starve to death. Which, if you're a philosopher, is hard to argue with, even though you intuitively feel that won't be the case. You can say, well, a small puff of breeze will cause it to go this way or that way, and the result of that will be an asymmetric thing, which will be that the donkey has eaten this bunch of carrots, so there'll be a nicely fed donkey on this side and a bunch of carrots left on the other side. But what you've done is you've introduced something which is asymmetric. You've said, oh, maybe a puff of breeze did it. Yet you know in your heart that something has to happen. But for a philosopher, it's an interesting question. Perfect symmetry, how does it happen? Well, let's move it along to a next level, which is if you go to some very fancy banquet or you go to the captain's table on some transatlantic liner, you sit down at this circular table, which has been perfectly laid, where you are each symmetrically oriented around it. Your table napkins and plates and things are all there. And you now have the problem, is the table napkin on the left or the right the one that belongs to you? Well, what will happen is that somebody who is slightly more aggressive than the rest will break the symmetry by picking up the one on their right, and you'll get a wave of right napkin grabbing going around the table, and the meal can start. Okay? What then becomes interesting is if we make this even bigger, let's imagine you've got 800 people around a table. Then what can happen is that over there, you, sir, grabbed a napkin on your left, which caused a wave of left napkin grabbers to come down that side of the room. And that lady over there picked on the right, making the right wave come round here. And then you get something interesting happen. You have got no napkins at all, and you have got two. And this is an analogy for what actually happens in metals that become magnetized when you cool them, that you've got little magnetic atoms or molecules wobbling around at high temperature every which way. You start cooling it down, and not all will be jiggling at exactly the same rate as the distribution. And two that are moving slower than the average will sort of lock in on each other over there, making North Pole that away, causing this right napkin grabbers analogy to make lots of North Poles down this side, whereas you lot will perhaps be linked into two over here, making them over that side. So you get domains of magnetism with a dislocation down the middle. So this is a very well-known phenomenon in solid-state physics and magnetism and many other places as well. But even then, you sort of feel, yes, but, he's sort of set this up in an artificial way. That's because the atoms were jiggling around, and that's what broke the symmetry. What happens if I lower the temperature so that I go right down to absolute zero of temperature where they're not moving at all? Then what happens? Then what happens is that the quantum gets you. You can't both localize the atom precisely and know what it's doing. So however you try it, the fundamental uncertainty principle of quantum mechanics at the end of the day forces things like this to happen. So what is the common feature that's going on? Oh, well, shopping trolleys is another one that we all know. You push as carefully as you can, pushing your shopping trolley or the one in the airport, and it gets a mind of its own and goes every which way. Okay? what is happening is this in all of these examples. You have got a situation which I've sort of illustrated. I had that Buridan's ass at the top of that hump, if you recall. If you've got a ball balanced at the top of the hump, it is metastable. The slightest disturbance will make it roll one way or the other. So it is a nicely symmetric configuration, but it's not the most stable one. Come in, Tony, you'll learn something here. So what you have is you're making a choice. I can have a highly symmetric but unstable as against an asymmetric and more stable. So each of those examples that we looked at was giving up symmetry for stability. And it's chance that it went that way or that way. So this is the background to the idea that was going on with these gentlemen that I told you about earlier. The attempt to build a theory linking the electromagnetic and the weak forces, which starts off beautifully mathematical if you pretended that not just the photon, but all of these other beasts had got no mass at all. That's the perfect symmetric case. And what you want to end up with is the real world where the W particles are massive. So the analog is that that is, in some sense, more stable, even though it's not symmetric. So you want to try to use this idea of hiding symmetry by this sort of game to introduce the mass. So what does this all mean in reality? How do they do it? Well, at first sight, you get the impression that you can't do it. Let's just think of this really as a ball sitting on the top of this hump. And the ball can roll down any way. Or it could roll around the bottom anyway, because it could go from the hump on the east direction or the west direction or the north or the south or anywhere between. If it's the snowflake that is forming, it could have started off in the 12 o'clock position or slightly off it or anywhere between. Each of those individual snowflakes is as good as the other. And all you're doing to go from that picture to that picture is just rotating your head a bit. It's called a global change. Everything in the universe just rotates a bit and you appear to have gone from one to the other. It costs you no energy to do it. And in the real world analog of quantum field theory, going from one configuration to the next around the bottom of that rim, where they've all got the same energy, corresponds to a wave going around there with no energy, like the napkin grabbing. And a wave with no energy corresponds to a particle with no mass. And it turns out that this would have to be a particle with electric charge in these models with no mass, and such things do not exist. And that, in 1961, was thought to put an end to the whole thing. Very nice idea to try to use these things and apply them in field theory, but unfortunately, nature doesn't do it that way, end of story. Except it was then discovered that there was a loophole, and that if, in addition to the little picture we've got here of a ball rolling down the slope, there were long-range forces present, as is the case if you've got massless things like photons or other particles around, there was a loophole. It's become known as the Higgs mechanism, except that it isn't the Higgs mechanism, because there were several people that knew of it before. One of them, especially tragic for our story, because it involves Jerry Guralnick and John Ward. And it's this, that in 1964 we saw John Ward and Salam at the top there, building their model of the electromagnetic and weak interactions built around this SU2 times U1 structure. But they didn't understand maths, they were just ignoring that. Meanwhile, in the very same institution, Imperial College in London, Jerry Guralnick, who knew nothing at all about SU2 cross U1 and such like, was interested in how to get mass into theories. And he had solved that one. One day, he and J.C. Ward went to lunch together. Now, Ward was quite a senior physicist at that time, and Guralnick was a young postdoc. And so I imagine somewhat nervously trying to get a conversation going. But Ward was quite a sort of suspicious character. And Guralnick had hardly started speaking before Ward said, "Have you published these ideas? Have you told anybody about them?" And Guralnick said, no. Then stop speaking immediately, because people will steal your ideas. And so Guralnick stopped there and then, and didn't dare ask Ward what Ward was doing. The result was that they left that dinner party, Guralnick being totally unaware of SU2 cross U1 and Ward being totally unaware of how to put mass into it. If they continued talking another 10 minutes, the pair of them could have solved the whole thing there and then, and they would have probably shared the Nobel Prize many years ago. But that is not how it happened. What we have happened is that there are, in addition to Guralnik, this group of 6 people, all of whom, in the space of a few weeks, came up with the same way of getting around the what became known as the Goldstone boson problem, how to give mass to things. And this is what the Gang of 6, as they're now known, are. And the papers in which they published the ideas were published over a very few weeks. And this, as you look on the top there, Phys Rev Letters Volume 12 obviously comes before Volume 13, and page 321 obviously comes before page 585. So that is the order of priority you would expect these people to have if you read Stephen Weinberg's 1971 paper. If, however, you look at another paper a couple of years ago, every 2 years, there's a big sort of book published called the Particle Data Tables, which has all the information about particles in it. And they have little mini reviews. And one of these mini reviews was reviewing the whole business about the Higgs boson, or whatever it should be called. And they have got the references in there. Let's just flick back and forward. You see the top two. In Weinberg, it's Phys Rev letters. And in this review, it's physics letters. In fact, neither of these is correct. That is the correct one. There was interesting people who like to be sociologists or trace Darwinian evolution. You can go through the literature. Weinberg's paper has been cited several thousand times. It's one of the most highly cited papers in the subject. And this incorrect reference has propagated through. It shows that people reference what other people have referenced without actually reading it. And so it gives the impression that Higgs did it first, whereas in fact the order of events is that Broughton Engler published first on the 26th of June. Higgs completely independently wrote the same basic ideas down on the 27th of July in a different journal. And then Guralnik, Hagen and Kibble independently, although by that stage these papers were now out there, published in October that year. If that was the whole story, then you might wonder why the Higgs boson is called after Higgs. The answer is because I'm not talking about the boson, I'm talking about how you give masses to particles. So what's the boson got to do with things? Well, the boson in Higgs, let me just go back, Higgs wrote 2 papers. The first one, the 27th of July, showed how to give mass to things. On the 31st of August, he wrote a further paper which included what we now call the boson. I asked Broughton Engler, why didn't you include any mention of the boson? And they said, well, we thought it was obvious. And indeed, it is everything is obvious with hindsight, of course. But to be fair to them, the examples that I gave you, first of all, about hidden symmetry and spontaneous breaking of symmetry, I said, magnetism, the magnet's little locking in, that phenomenon was well known in condensed matter physics, which is what Broughton Engler's speciality was. In that field, the analogues of what we call the Higgs boson were already known, and these people indeed regarded it as obvious. They didn't draw attention to it in particle physics. Guralnik, Hagen and Kibble, in their paper, they implicitly have it, but they also don't mention it. The only one that mentioned it was Higgs, and he agreed with Broughton Engler. It is obvious, but he mentioned it. Now, you might say at this point, well, big deal, so what? Well, there is an interesting so what here, which is the punchline that we're coming to in a moment or two. So let's just try to tie up what has happened with what I call the bosons. This picture of this, whether it's the base of a wine bottle or a Mexican hat, whatever you call it, just think of it as a realistic case of a ball sitting at the top of some gravitational potential, which is in this highly metastable configuration, but can spontaneously, through some slight perturbation, drop somewhere or other. It can drop into the rim, and the issue back in 1961, before all this was sorted out, was this problem that the ball could be anywhere around the rim, and to rotate from one to the next cost you no energy, and that would correspond, in the field theory example, to the presence of what was known as a Goldstone boson, a massless thing which does not exist. And the problem that the Gang of 6 were all trying to solve and did solve was how to get around the problem, how to get rid of the Goldstone boson. And they found that it was indeed possible to do that in the presence of massless fields like the photon, and giving them mass. And that was the solution of the gang of six. What they were focusing on totally was what happens when the ball rolls around the bottom of the rim. Higgs alone pointed out that there are three dimensions here. The height of it is the potential that's making the ball roll. There's the there's the angular one, which they were all worrying about, but there's also a radial one, where the ball can roll up and down the base of the valley. The ball rolling up and down the base of the valley, in field theory, corresponds to a massive boson. Higgs was the only one who drew attention to that. So in a sense, it was trivial. But the point about it, though, is it's incredibly important for testing whether the whole idea is really how nature does it. And that is what has led to the boson that's named after me, as he calls it. And the paper where he actually really gets to it is 2 years later in 1966, because that is the one, I think, that's started off the whole of the excitement in particle physics for the following reason. What we have had through this talk is this whole background, the idea that the forces of nature are described by a common mathematical system with one feature, that mass gets in the way to spoil it. We discovered that the basic particles of nature seem to have a symmetry to them, except that mass spoiled it. And that all of these people found how to get mass in by this particular trick. But only Higgs realized there's a further implication, the presence of a massive boson, and this is the key feature. It's all very well to write down mathematics that does beautiful things, but how do we know whether nature actually does it that way or not? You have to have an experiment to test it. And the point about this massive boson of Higgs is this. If it's the case that the mass of the quarks and the electron and the W and Z is due to what I would call the mechanism, the mass mechanism, it's the decays of this highly unstable massive boson that will test whether that is how it works or not. This boson lives, if it exists, it lives for a very brief moment and decays into things that you can detect. The relative amounts of different varieties of quark or of electrons and muons or W's and Z's and so forth will test whether their mass has really come from this mechanism or not. That is why searching for the boson is critically important. That is the only way that we know how to test whether this whole idea is what nature does or merely what mathematicians have done. So that's why finding the boson that's named after Higgs, I think, is the key to the whole business. So to end, that is what the Large Hadron Collider is attempting to do, among many other things. I just thought I'd show you quick 3 cartoons of the Large Hadron Collider, each of which are totally uninformative. The first one is, that is an artist's impression of a tube going around under the ground and a detector where the beams of protons smash into each other to create the conditions where, if you're lucky, a Higgs boson might appear. If it does appear, you've got to be able to identify it out of a host of other things. You have these huge detectors. This is an artist's impression of the sort of collision that's happened in the middle of a detector. Huge detector here. I've no idea what these things are, but they look like sort of trash bins that have been placed down the bottom of the thing. And then the picture you keep seeing in the media all the time, which shows the Atlas detector, very impressive. But actually, of course, that's not the Atlas detector at all. It's completely empty space, which is now filled by the Atlas detector. But anyway, that's how it goes. But that is definitely Peter Higgs, standing in front of another detector, which always reminds me of, I think it was Alfred Hitchcock who claimed that he was the first person to get sex on the screen behind the train going into the tunnel, and that looks somewhat like that. So I think the summary of it is that how nature builds the boson, or whatever it is, and performs the magic, only nature knows. I think that the fact that the work that Weinberg, Salam, Glashow and Ward did in building this model of the electroweak force, ignoring mass, when you combine it with the mass mechanism that these 6 people found, gives you the possibility to build a complete quantum theory, which is what 2 people who I haven't mentioned today but are mentioned in the book in great detail, Toft and Veltman, managed to do. They produced from that a quantitative theory that has been tested now to about 1 part in 10,000. And it works. the fact that it works using these ideas means that either these ideas are how nature really does it, or there's a huge conspiracy going on, and I don't believe in conspiracies. So I don't think that many of us have any real doubt that this is the way that nature has done it, but the details of how nature has done it, I haven't got a clue. Whether it's just a simple, single, massive boson, as Higgs said 50 years ago, well, if nature's done it that simply, it'd be very much surprising, though it's possible. In that 50 years that's happened since then, we've got much more insights about phenomena and the possibility that there's a whole family of things called Higgsinos and everything else like that could be the case. It's possible that the Higgs particle is not a fundamental thing, but it's itself a composite of other things called techniquarks, or maybe something else. The exciting thing about science is I'm pretty sure that something is going on and that we are in the right regions to find out what it is, but at the moment, only nature knows. Once we know the answer, I bet it'll be as obvious as everything. But if it was obvious now, I'd be writing it down. That's what the exciting thing about science is. So that was really one part of the story, but only had the 40 minutes today. I don't have another 5 hours because my voice wouldn't last more than 2 minutes more. So thank you for that.